Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to be building up a PCB project. And it's this. These are all the parts for the RCTP, or the Retro Chip Tester Pro. I showed this thing on a Super Mini Mail Call video on the second channel recently, and I'm going to be using this to try to test some of the ICs in the TRS-80 Model 2. That's what I'm pointing to over there. I'm hoping that this thing is going to be useful in trying to figure out what's wrong exactly with the TRS-80 and why it's not starting up. So, without further ado, let's get right to it. So on the bench I have the soldering iron, I have solder, I have some wick to clean off the tip, I have one of these things here to hold a PCB, and typically when you use one of these things you need to use some tape over the components so when you flip it around all the parts don't fall out. And in case you haven't watched the Super Mini Mail Call video, the lovely viewer that sent in the Retro Chip Tester Pro bagged up all the parts for it, so everything I need should be in here, every single part. So I'm going to load up the build instructions on the computer here, and I'm going to set up the cameras for a little bit of a time lapse. Sit back, relax, and enjoy about 5 hours of work in about 5 minutes. If you want to skip over this part, click the time link in the description. Assembling large projects like this requires you to be really organized. It was super helpful that all of the parts for this project were already individually bagged, so I didn't need to sort those out first. The bags all were labeled with exactly what the parts were inside as well. I worked one build sheet at a time, making sure to take inventory of all the parts that were bagged and match them up to what was on the build sheet. I also marked on the build sheet any time there were more parts in the bag than were required, which meant I would have spares. For a project that has a lot of the same component with the same value, I tend to just install all of that one component at once. As an example, in this project there were a lot of 470 ohm resistors, so I counted up on the build sheet how many there were. I made sure I had that exact amount ready to go on the bench, and then I installed them all in the board, making sure that I had none left over when I was done. For components where there's only a few or a couple or even one of each, I will batch those together, but I make sure I mark it off on the build sheet so that I keep track of exactly what I've installed. And in this case, I also put a check mark on the bag that the component came in just to make sure that I know that there was nothing left. I also make sure that I take the bag once I'm done with it and I put it on the floor or take it off the bench so that I don't get confused later on. This PCB was also marked with the values of the components that went into it, or in the case of diodes or transistors, the part number. The layout of the board was also very logical, making it very easy to find the component locations. You'll notice I'm using those magnetic trays used for car repair, and you can pick those up at the auto parts store. I really recommend them to hold things like the offcuts or even the individual components. In the case of this project, I was supplied with usually the exact amount of components required for each type, so the magnetic trays came in really handy to make sure I didn't lose a part on the floor or something. Here I'm finished with the first sheet and I'm admiring how much work I actually did. Now it's time to start the second page, so time for another inventory of the parts. I really have to thank the viewer who sent this in because every single component was perfectly bagged and there was not a single thing that was missing to build up this entire project. Here you'll see I'm using painter's tape or sometimes blue tack to hold components into the board as I flip them over. For things like resistors and diodes, I'll bend the leads so they'll stay in place, but sometimes the leads are too short to do that, so that's where these other things come in handy. There were 3 types of TO92 packages. Those are the little packages that transistors typically come in, and the board was very clearly marked for which type of package went where. The leads of the transistors are relatively close together on the board once you insert them, so soldering them can be a little tricky just to make sure you don't create solder bridges. The only small issue I ran into when building this was there was one bulk capacitor on the power supply rail, and it's under the LCD screen. And the way the instructions tell you to install it is standing straight up like you normally would. But when I test fit the LCD screen, I found that the capacitor actually hit the bottom of the screen. So I had to remove the original capacitor and install a new one with it lying on its side so it wouldn't hit the screen. I really have to applaud the creator and/or maintainer of this project because the assembly instructions were very clear and it pointed out a couple of the little gotchas you might have with very clear photographs. So thank you very much for the wonderful documentation. And the final step is to install the SD card module, which with the default pins on it, actually would make it stick straight up off the board. So I desoldered the original angled pins and installed some perpendicular straight types so that when I stuck it onto the connector, it would lie flat against the tester. Okay, build is complete. I ended up going with the number 4 DC to DC converter. There were 3 different options, but this one appeared to be the most capable. How about I peel off this tape off the screen? Oh yeah. Oh yeah. There it is. I appreciate that there's a volume potentiometer here for the buzzer so you can turn it down if it's annoying. Normally you'd have to stick tape or something over these to shut them up. I did end up with these extra parts, like there's this 6-pin header here for ISP. Is that what it is? In-circuit programming? Yeah. I had one with a shroud, so I installed that instead. On the underside, I haven't cleaned it yet. I figured I will do some quick testing, make sure it works, and then I'll try to clean all this flux off the bottom of the board. You'll notice that I installed all sorts of connectors for power input. There's a micro USB, a regular size USB, and then a DC barrel jack. If you don't have the DC to DC converter and you need some voltages that aren't provided by it, you can use these screw terminals here for 5 volts, -5 volts, and 12 volts. I'm just giving the board one more inspection on the bottom, make sure I've soldered every connection and nothing is shorted together. Looks like I only soldered 1 pin onto the header for the micro USB card. And that is it. I think I'm really ready to power this thing up now. For the first power up of the board, I'm going to use my bench power supply at 5 volts limited to 500 milliamps. That way, in case I have something wrong and there's a short, I'm not going to put like 3 amps into this thing and blow it up. The manual indicates that this is center positive, so I'm just double checking that I am putting 5 volts into the positive pin. And I guess we're ready to go. I have the power turned off, so we'll slide that into the barrel jack. And here we go. All right. Well, the screen lit up, but we're not seeing anything, but that's not a problem. There is a little potentiometer here. So let's adjust that. Uh-oh. All right, well, if I turn the potentiometer all the way to one side, it does work. But boy, this LCD is hard to read. And also, the backlight is sort of flickering on it. Okay, I think I realize the problem right now. The actual input power right now is 2.1 volts at 500 amps. So obviously the DC to DC converters are doing their thing because the microcontroller is running, but I'm going to need to increase the current a little bit. Okay, there we go. Now it's working properly. Power supply is putting out 5 volts now at 328 milliamps. I don't know, it got kind of stuck in a weird current limiting mode. Well, it's cool to see that the DC to DC converters are doing their job. They were creating a 5 volt rail even though no 5 volts was available on the input. Anyhow, as you can see, the microcontroller is absolutely running. Let's see if I can figure out how to use this. Reset. Okay, there's the firmware. I probably need to update the firmware. All right, see the interface, there's a select and a jump button that seems to kind of go back and forth in this menu. So Cypress and between uncommon and Cypress. And then when you hit OK, it actually goes into that menu. So if we go to DRAM common, now we have 2104, 2107, 4116, 2118, 4416, and a 4164. This is very typical for the Commodore 64. Well, now that I know this thing seems to be working, at least from a rudimentary standpoint, I'm going to figure out how to use it, and then I'll come back and show off what it can do. All right, it is the next day, and I've had time to get to know this thing, and boy, do I like it. It's pretty amazing the amount of things it can test. So no more bench supply. I'm going to be powering this up from my USB power bank. So the micro USB connector on the side is extra useful. There it is. Now, right off the bat, one thing you may notice is that the screen is much brighter and much more readable. A couple of reasons for that. First of all, I switched out to a different LCD module. I found the one that was included with this thing was just not a very good LCD. It had very bad viewing angles, and the contrast overall was just not good. But even with this one, which is a little bit better, the backlight brightness was incredibly bad. Well, it turned out that under the LCD was a 220 ohm dropper resistor in case you were using a screen that didn't have a built-in dropper resistor. This one and the other one I did both have dropper resistors on board, so you just hook 5 volts directly up to the anode-cathode connection for the backlight. So what I did is leave that resistor in place, but I simply jumped it right here with a little piece of offcut, and that bypassed it, allowing full 5 volts to go to the backlight. Let's try testing a few things. I haven't even done that yet on video. I have a couple RAM chips here. Both of these are 4116 or 16 kilobit times 1 bit RAM chips. This one has a part number of 5290, but it's actually a 4116. Testing DRAM chips is not something I've ever been able to do because you need a dedicated tester that supports refreshing the chips. Not to mention, these particular DRAM chips require multiple voltages, not just 5 volts. Of course, with this fancy DC-to-DC converter, we have 12 volts, 5 volts, and minus 5 volts all available on this board. It has 3 different voltage rails, and there's actually minus 12 volts available right here. So in conjunction with the voltage regulator, you can get the necessary voltage that some other ICs use if it's not the 3 that are provided. Of course, this type of DRAM uses these 3 rails, so that's all available right here on the socket. So we go over to DRAM common, and then we select 4116. It shows that this chip is using 3 different voltage rails, and with the chip inserted in the socket, we just push OK, and the testing begins. And there are some relays under here, under the SD card, that switch in the appropriate voltages to this IC. And there we go, test pass. So I'm going to draw a little tick mark on there, just so I know that's a good chip. It's pretty sweet to be able to test these chips finally outside of a computer because I don't have something I can easily stick these into to test. They're typically used on really old machines like the Commodore PET, stuff from the late 70s and very early 80s. Next up, we have another DRAM to check. This is a 4464 chip, means that it is 64 kilobits times 4 bits, as opposed to a standard 1-bit chip like these. So when you're at this screen, just hit any other button and that exits out. And we can go select the chip we want, 4464, 64 kilobit times 4, and hit OK. What's cool about this tester is it doesn't send voltage to this socket until the test begins. And you'll see this light down here turns on, the VCC light. So that means that you don't risk shorting anything out while you take chips in and out of the socket. All right, this chip passed as well, so I'll put a tick mark on there. Now for the video, I sped up the test cycle so it happened a lot more quickly. But if you think about the speed of the test compared to the 16K by 1 chips, there are 4 bits here versus 1 bit, and there's also 4 times the size, right? 16K times 4. So it takes about 16 times longer to test this chip than it did this one. So this tester is not really ideal for large-scale testing of tons and tons of chips. But for quick testing before I install something into a machine, it's pretty good. All right, how about a venerable 4164 chip? This is typical for what's in a Commodore 64. So we just go back, 4164, and hit start. All right, another good chip. So I'll put a check mark on that so I know it is good. All right, so testing regular DRAM chips, it's cool, but it's certainly not all this thing can do. How about testing this? It's a SIPP, a 1 megabyte SIPP. I have no way to actually test these except for sticking them in a computer that uses SIPPs. I think I only have like one old 386 motherboard or 386SX motherboard that uses these. But how exactly am I going to test this inside this socket? Well, with this, which is one of the adapters that was included with this thing. Plugs into the 32-pin socket here, and then it gives you access to both SIPP and 30-pin SIM testing. Now from reading the manual, it only supports up to 1 megabyte module. So you cannot test 4 or 16 megabyte modules. I assume that's just a software thing. Also though, the testing even for the 1 meg is very slow. So a 4 or 16 meg module would probably be excruciatingly slow. So we just stick it in just like that. Back in the main menu, we scroll to DRAM uncommon and we scroll through the various choices here. And there it is, 30-pin SIM P for parity, and there's also one without parity. And it supports the 256K version as well. So we're gonna pick parity because there are 9 chips on here, there's parity, and we're gonna hit start. And there it goes. Now we wait. It's a very slow test. If you think about this, has 1 megabyte times 8 compared to the very slow test, where is it, of this 64 times 4, that's 64K times 4. Well, there's a lot more memory to test here. While we test this SIPP in here, let's take a look at this database that's included. This is actually a file that comes with the documentation and it's not online. So you can copy this onto your phone or your tablet so you can just access this at any time, even while you're off the internet. You just type in whatever IC you're looking to test, so 75245. This is of course an octal bus transceiver and it says it's supported as of version 14 of the firmware. I have version 19 on this device right now. It also lists alternative part numbers that it can test under the same profile. So I just have a sheet here full of some chips. Let's just type in a couple of these part numbers and see what can actually be tested on here. 573, let's see if that can be tested. I'm not even sure what that chip is. And there it is, 573 is an octal D latch and that's worked since version 15. Here's an LP339N, whatever that is. Doesn't seem that this is actually found. Let's just quickly look up what this chip is. All right, no wonder why you can't test this. Analog comparator. Yeah, that's impossible to test because it's an analog circuit. How about this chip here, the SN74156. This chip is from 1971, super old. No idea what that chip is. 74156, dual 2-line to 4-line decoder multiplexer with open collector. It's working since version 15. How about the 74LS163? That's a synchronous 4-bit binary counter with synchronous clear, working as of 19. So that's this firmware that it's on here. By the way, this is still running the test. So that means that stuff is routinely being added all the time. Why don't we grab that chip for testing along with this 1971 IC here. Speaking of firmware updates on this thing, I actually tried to update to the latest firmware, which happens to be version 20, and I ran into some issues. There's actually no way to update the firmware on here using the micro SD card. You have to use this ISP or in-circuit programming port with an external Atmel programmer. I had a USB ASP little device. Turns out that that can't program the ATmega 2560, which I think is the controller that's used on here. That little device is just so junky that it can't work properly with this. So I've gone ahead and ordered a new programmer which is confirmed to work on this so I can update the firmware. I was about to talk about how good the documentation is in here, and to be honest, I thought I read most of it, but it's 170 pages long, and it actually talks about using the Arduino as an ISP. So obviously I have an Arduino Uno lying around. I could have used it instead of trying to get that silly USB ASP working. This is the programmer that I ended up ordering, which is good because I wanted to actually have a good AVR ISP device so I wouldn't have any issues trying to load bootloaders next time. Okay, the SIPP has passed, so this is a good module. Excellent. So I'm just gonna draw a 1 and a tick mark on there so I know it's good. That was probably 10 minutes from a time to test perspective, and I'd have the march up and down tests disabled in this thing. It would have taken longer if I had them in there. If you've watched any other videos on this tester, like on Noel's Retro Lab, you've probably heard people complain about the fact that finding stuff in the lists can be a little tedious. And for the DRAM and stuff like that, it's not so bad. But for the logic chips, there's a lot of them, and it's probably going to be a little bit tedious. So I think this menu here is for the lower number 74LSs, and this one is for 500 plus. Anyhow, let's go into the logic test. Okay, so this is the 74LS163. So now we just have to scroll through. Now I can hold the button, which is what I'm doing now, and it's, oh, okay, it went by pretty quick there. Let's see here. Okay, it starts jumping, I see. The longer you hold it, it jumps quite fast. Okay, that's actually not bad. There's like an acceleration going on. Okay, here we go. Yeah, it starts going by tens. Okay, not bad. That's actually better than I thought. Okay, there it is, 74-163. So let's stick that in. Close the tester and hit OK. There we go. It looks like it does about 15 tests, and that's good. So as you can see, the date code, this is from 1977. Good old chip there. But let's test this really old one, the 74 156 from 1971, older than I am. So we just hit no for no more tests. And we scroll down to what it is here, 2 to 4 decoder. Oh, that's amazing. A working TTL chip from 1971. I'm just gonna draw a tick mark on that and a tick mark on this. So back to the menu. If you push up or down, it's pretty responsive, but if I hold it, you see it's going one at a time, and now it's going 10, I don't know. It's going really fast. So there are like 500 chips in here. Maybe there's not 500, but you just hold it and okay, you know, this is actually a lot better than I thought. Maybe it accelerates a little too quickly. No big deal. You just let go and hold it again to not go too quickly. All right, so one of the things is also for this particular board, there is no back button. There's up and down, okay, and there's a reset button. Obviously, reset will take us completely out, resets the whole device. On the newer versions of this board, there's actually a 5th button that is like a back button or an escape key. This one has provision to add that. There's actually a pin right there next to this LED, and theoretically I could put a button here. You just have to ground that, and it's the equivalent of pushing back. But there's actually another thing I can do. I can just push these 2 buttons, the up and down at the same time, and it takes me to exit, and I just hit OK. And that backs out as well. So it's an extra push, you know, it's 2 buttons and then 1 to get out versus probably just pushing 1 button. But I actually don't mind that at all. That's a pretty creative use of this firmware. And also what's cool is you notice these buttons are the tall versions. You don't actually have to push them straight down. You can actually tilt them over. And that makes pushing 2 at the same time very easy. You just use them like piano keys. So that's pretty a cool little trick. I didn't know that, and I actually talked about that in the documentation. All right, next test. Let's test some SRAM. This is a 2114, which is a color RAM on a 64 and also video memory on the Commodore PET. Very common, and they seem to go bad quite a bit. So we go into here and 2114, there it is, 1K times 4-bit. Hit test. This should be pretty quick because there's not a lot of capacity to this chip. There we go, that is a good chip, at least according to this tester. Excellent. All of the chips we're testing here I have not tested before, so this really is first time testing, and that's why I'm marking these. Since I'm testing them, we might as well see if they work. Next up, we have some cache memory from like a 486 or something, the 24257AK chip. Now because that's kind of a weird part number, let's go to the database and look it up. 24257, not found. There, all right, I had to add the W, so it's a Winbond W4257. This is actually a Winbond branded chip. It's an SRAM 32x8, status supported. Select XX256. So let's look in here for that, XX256, 32K times 8 bits. There we go, let's hit the button to start, and now it's testing. So I have to say this searchable database is extremely handy because like I would have never figured out that this particular chip is actually the XX256 profile if I was just looking through these menus for the test of this chip. Included in the documentation are actually the extensive and full lists of all the supported ICs. So if we open up the SRAM one, when you look up a particular IC, it tells you what profile you need to be using to do the testing. Some of them will say custom because yes, you can actually load custom test parameters for ROMs, SRAM, and DRAM onto this. Not for logic right now, but at least for those other chips. You put the profiles onto the SD card, and when this thing powers up, it'll actually load that into a custom menu on here so you can test it. There are only a few slots for each type available, but it's a super handy feature if you want to define custom chip types to test in here that maybe are rare and no one's ever heard of. So this IT, as you can see, has tested good. So it gets a tick mark. Thank you very much. My little pile of good chips is growing over here. All right, here's another SRAM chip to test. I think this is the type that's in 1541 disk drives. It's like 2K of SRAM. And there it is, SRAM 2K/8, and you use the profile XX16. And look at list all the various part numbers of compatible chips. XX16 2K/1, and hit OK. It's going to test a lot more quickly than the one we were just doing a second ago. So you can see it writing and reading, and there we go, tested good. Excellent. These chips seem to be very reliable. Here's another SRAM. This is a larger one. I think this one is 32K, It has the same pinout as a 27256 EPROM, if I recall. It's the HM62256 ALP-10. Yep, there it is, the Hitachi HM62256 XX256. So let me show off a couple of the other interesting adapters that exist for this. This one here allows you to dump Atari 2600 cartridges. Although I can't demonstrate this because the cartridge actually won't fit over this. You have to take it out of the case and then just stick the PCB directly into here. So that chip passed. So we'll put a tick mark on here. Excellent. Another good chip. So let's take a look at another adapter that exists. This one here is for dumping Commodore 64 cartridges. It has jumpers, or actually normally you have a toggle switch, but I didn't have the right one to install, that allows you to dump the high and the low portion of the cartridge. Standard cartridges like this on the 64 are either 8 or 16K. There are some that are larger, but they use some bank switching methods, which is not compatible with reading with this adapter. You're gonna have to take the cartridge apart and remove the chips and actually read them directly on here. Well, let me just stick this on the cartridge and let's give this a try. So I'll have to read this twice on both of these settings. I'm pretty sure this is a 16K cartridge. And we're gonna use this setting right here. Now, if I just push the OK button, what's gonna do is it's gonna read the cartridge and it's just gonna calculate a checksum. But if I hold down the OK button for longer than just a quick push, it'll actually save the contents onto the SD card. And there it goes. And there it is, saving the 2764. It will still calculate the actual checksum. Now, one thing I'm noticing is that that checksum, I don't think matched the first one. Let me just do another read out of this thing. No, that is not right. Okay, so I guess this is not working very well for some reason with this cartridge because we keep getting a different CRC. Now, with reading the documentation, apparently sometimes the old chips in these need more voltage than this thing is giving through all of this switching circuitry. And in that case, we could use something like this. This adapter, which plugs in and then has another ZIF socket, has all of these jumpers, which allow me to disconnect the VCC and the ground lines from this switching circuitry and just feed it directly off this header right here. I did just notice though that I'm not going to be able to use this because unfortunately that ZIF socket is the smaller type and that will not go in there. I think one of the problems is by the time the 5 volts from the DC to DC converter gets to these pins, it's gone through transistors, and there is voltage drop through transistors because they're being used as switches. I think you're getting around 4.8 volts, and that may not be enough for older chips like this cartridge. The manual talks about these issues, and that's why you have these decoupling adapters. With this adapter, what's neat is you can just remove these jumpers, which disconnects the various pins on this ZIF socket to the one on the tester, and then you can put little jumper leads around here to rewire the way it's actually talking to the IC. In addition, of course, you can hook logic probes up to these various pins here, so you can also look at the signaling while it's being tested. As I mentioned earlier, I built up this version 4 of the DC-DC converter, but there's actually a version 3, which I'm going to build up as well, because one of the things that it can do that this one can't is it actually uses a configurable linear regulator that allows you to select which voltage it's going to output. And I think it has jumper settings for like 5.1 volts and 5.2 volts even, so that you can give this thing a little bit more voltage so that by the time it gets to the socket, it will actually be at 5.0 volts. So let me pop out this SD card and stick it in the computer. We can take a look at what it did read off that EPROM, which we know is going to be no good. This is the file right here. Load this into HXD. And looking at the code, you know, it looks like there's something there, but we know that it's not reading properly because the checksum keeps changing. On the card, you'll notice I have custom SRAM 1 and 2. Here's the custom definition for this particular SRAM chip, which is a 512K. It's the same chip I used on my Tandy 1000 RAM expansion. I guess this thing can test it. So this defines what it is here. It uses all 32 pins of this socket and then all the various signals. The manual describes very clearly exactly how to create your own files. Now, speaking of ROM chips, this thing is already configured to read all sorts of custom mask ROMs like ones used on Commodores. You can't just stick these mask ROMs into a Mini Pro. They are only really configured to read and write to EPROMs or EEPROMs, not these mask ROMs, which have slightly different signaling, especially when it comes to chip select lines. This one is the MOS 325-503-01 from 1983. I don't really know exactly what this is, so we'll just stick it in there. We're going to go over here to PROM ROM. Now, one of the things is you kind of have to know with this mask ROM how big it is so you could use the appropriate profile. I'm going to say most likely this is going to be a 2364, so it's an 8K ROM, and there are two profiles to use, a 24 and a 28 pin one. I'm going to use the 24 pin, that's what this is. We're going to hit OK. Next is a submenu asking about the selection logic for this IC. This is saying with this profile, which does say Commodore, when pin 20 goes low, that activates the chip. I can switch to the next one where it goes high, it activates the chip. Doesn't say what that's for, but maybe certain mask ROMs use that logic. And then there's also jump to detect. Let's try that. Okay, it detected it. It says low 20. So of course this is a Commodore chip, so that makes sense. We're gonna hit OK, and it's gonna read this and calculate the checksum. Now there's the CRC. Let's try reading it again. Let's just make sure it's the same. Should be. I don't think there's any problem reading these. Yep, that's the same. Now on my SD card, which I took out because it was in the computer, there's actually a little database that was included with this, and it's like a checksum database. So if we try this again, it might read the card and maybe tell us what this is. Using index file, there it is. Commodore 1540 disk drive. And there's the ROM, 325-503-01, 325-503-01. It worked, and this chip is a good ROM chip as well. The database that I copied onto here is actually the entire MAME database of everything that MAME supports. So if the ROM is in MAME and it's had its checksum calculated, if I read it out on this thing, it would tell us what that is. How cool is that? Oh, and let me demonstrate saving this onto the SD card. So I push this and hold it, and it's gonna ask us about the state, and there it is, it's saving. Uh-oh, oh, that's weird that EPROM is empty. What happened there? Let's try that again. Let's just read it quickly. Okay, so when it has zeros, it's empty. So that's working. Maybe that's a bug. I'm gonna hold this down. There we go. No, it's working. I think I just had a bad connection in there. So there, it created a bin file that's the name of the checksum. It might have a text file as well. Let's just check it out. So there's the bin file, that's the dump of the ROM, and it created an associated text file. And if we open this, it's the text that was displayed on screen. So that's very handy if you want to dump several chips, and they are in the index. That way you don't have to go writing down those checksums. I happen to have another ROM here, it has a tick mark on it. This is from a C64, active state Commodore, Commodore 64 NTSC. That is so cool. So I'll put a tick mark on that. All right, here's another test. How about a PLA? Now this is a Russian PLA. Well, it's a Russian chip that was programmed to be a PLA. It's compatible with the old 82S100 on this. So we'll stick that in there. I think the PLA test is under logic because this is a logic chip. There it is, Commodore PLA, 906114. There's two in here. And the 251641, that's from maybe the C16, the Commodore 16 and the Plus 4. This is the one for the 64 though. Let's hit OK. There we go, so that chip tested good. I mean, I knew that of course because I just took it out of a working machine, but very handy that this can quickly test your PLA for you. Of course, just putting a PLA into a Commodore 64 has that effect as well. But if you happen to buy one and you wanted to make sure that it's good before you stick it in your computer, well, stick it in this thing. All of these resistors and Zener diodes protect the microcontroller on here from shorts if the chip is bad. Okay, so I've tested a bunch of chips already and I've shown that this thing is really cool and really useful. How about we try to read a chip that I've never been able to read before? These here are Intel 1702A EPROMs. The 1702 was one of the very first EPROMs ever released. Of course, Intel did create the EPROM. And on the bottom, these are from 1978, which is pretty far into their life. I think they came out in 74. I don't even remember how big these are. Maybe they're like 512 bytes or something like that. But the problem with these is that they require weird bias voltages. Specifically, you need -9 volts. Well, this tester can't normally produce the -9 volts that this thing needs. So of course, there's an adapter for that. This is the adapter for the 1702. And what it has on it is a 9 volt or a -9 volt linear regulator. And you connect these leads directly to the DC-DC converter because it actually has a -12 volt output there, and you hook it up to the ground right here on that header, and then that powers up the -9 volts bias to the chip so you can actually fully test it. So with the adapter connected, but the wire's not connected to anything, there's no power going to the IC right now. So I can safely insert this and not worry about any kind of damage that might happen. So with these 1702s, I actually have several others. I have no idea if they work. I have no idea what's on them. I mean, they have these labels that just mean nothing to me. So it'll be interesting to see what's on them. We'll actually dump them. All right, so we're gonna get the minus 12 volts, and that should be going to the chip right now. I'll just scroll through the various ones. Here it is. Requires an adapter, 256 bytes. Okay, so that's all this thing is. We're gonna hit okay. Okay, it read it out. Let's see if it reads it consistently. Okay, checksum is exactly the same. I'm gonna hold this button to dump the contents. So I need to look for the file 44D. Let's do this other chip quickly. I just unplugged the 12 volts and then take this chip out safely. Now remember, because I've unplugged this cable here and the LED is off, there's no voltage going to this socket whatsoever. So there's no risk me shorting out things with this chip remover. I'm gonna plug the minus 12 volts back in and we're gonna hit test. Okay, there's the checksum. Let's check it again. Okay, it's the same, and then we're gonna dump it. There it is, it saved it. This is so cool. And here's our two files, 2E8 and 44D. There's no English words in this, but there's certainly not a lot of room in here. There most likely would have been a whole slew of these chips in whatever computer this was used on due to this tiny capacity. It's interesting, the contents of these two files is basically identical. Notice there's that byte, and I think there was one other byte that was different. Oh no, there's like 3 or 4 bytes that are different. So yeah, that's interesting. But that's one of the benefit of EPROMs over mask ROMs back in the day. Imagine if you were developing a computer and you were developing the software, the OS that ran on it, you had to keep having mask ROMs manufactured. So when EPROMs came out, even though you needed 4 of these for just 1 kilobyte, it was still so much faster than having ROMs manufactured if you're trying to test in actual hardware. Now, programming these is still a different matter. It's difficult. You need all sorts of weird programming voltages, but it's possible you can do it with this. Let me check the documentation. Okay, here it is. To program EPROMs, you need version 20 or higher of this device, which of course I still have 19 on here. So here's a picture of the adapter, and actually it looks like it has a little DC to DC power supply, a little boost converter on here with a potentiometer, so you can set the programming voltage. You probably do it ahead of time using your multimeter to get it close to the correct programming voltage, and then you can program these. That is so cool. So here's a picture of it programming the 2708, and currently I actually have some of these chips, but I have no way to program them. Even my Data IO 2700, which I think is one of the most capable programmers around, does not support the 2708. Looks like the 2716 is also supported with firmware version 21. My Mini Pro is actually one of the old first generation devices. The ones you can buy now are the second gen Mark IIs. This actually has higher programming voltages capabilities than the newer one, and this can program 2716. It's not quite up to the task because this can only generate, if I recall, 21 volts, and most of those chips need 25. But I have successfully programmed plenty of 2716s and they work fine. My Data IO, on the other hand, can program 2716s without any issue. But it is nice that this capability is here for people who have the newer Mini Pros who can't program 2716s. And then there's also support for the old 2532, which I don't think I can actually program these on any of the devices I have, although maybe my Data IO can program those. Looks like the adapter is for the 2716 and the 2532 together for both of these ICs. Currently, it seems this can only program those 3 types of EPROMs, but maybe more are going to come in the future, like potentially program these 1702s, maybe with the help of external power supplies or more boost buck converters on the board for that. I was lucky enough to get all these PCBs and the necessary parts to build up a bunch of other adapters, but when I looked through these various adapters, I didn't see any that I needed to build right now because I don't have any of these parts to even test with, so I figured I'll just wait until I actually need to test one of these before I build up the adapter. So what are my thoughts overall with the Retro Chip Tester Pro? I kind of love it. Minor gripes aside for like the user interface and the speed of some of the RAM tests, I think it's a pretty great device. It's staggering how many devices it can test. That database seems to be growing in leaps and bounds. I looked up some of the parts that I want to test from the TRS-80 Model 2, especially the bus transceivers in there. They're an obscure old part that's really not used in very much, especially these days. But of course, this thing fully supports testing those. The Mini Pro supports testing some logic devices, and the only reason why it doesn't have a bigger database is simply a software issue. I'm pretty sure this Mini Pro hardware is probably similarly capable as this thing is to testing stuff, but the software is just not well developed, so there's just no way to test so many chips with this thing. I'd say my biggest feature request for this, and I don't think it would be possible without a revision of this board, would be serial control of the tester. It would be really handy to be able to quickly jump to different tests using a serial port connection than having to navigate through the menu. Imagine you have like 50 different logic chips you want to test quickly. You have to scroll through all these menus to get to them. It's not exactly ideal. But I think if this thing had a functional serial port and you just plug it into your PC and you type in what you're looking for and then initiate the test from the computer, or maybe with a button push on here, it would just speed up that process so dramatically. But like I said, those are minor complaints, and this is still a very cool device. The build process of this was also excellent, as I pointed out during the time lapse. Very easy to follow documentation, very well designed PCB with very clear markings on everything. So I really didn't struggle putting this thing together whatsoever, as long as you stay totally organized and have all your parts ready to go. So with that, that sums up my thoughts on the Retro Chip Tester Pro. I'm really happy to have this thing. It's very exciting. I can't wait to use it some more for testing and troubleshooting on machines. And I really want to thank the viewer who sent it in, especially that incredible organization of all those parts. If you want to buy one for yourself, I'll put a link in the description below. This is not a sponsored video or anything like that, so these are really my thoughts on this device. So if you like this video or found it interesting in any way, I'd definitely appreciate a thumbs up. Check out the second channel if you haven't already. Thanks to my patrons, their names are scrolling up the side of the screen. I really, really appreciate all the support they've given me. And I guess that's going to be it. So stay healthy, stay safe, and I'll see you next time. Bye.